So my name is Boaz. I'm a founding engineer at MotherDuck, and as Robert said, we're going to talk about how to add analytics to Postgres. Just to kick it off, a little bit about me. So I'm leading the database group at MotherDuck. I'm Amsterdam-based, and before that, I've been a tech lead for the cloud platform at Elastic and a part of the Elasticsearch team working on the distributed aspect for a long time, and then history before. Obviously, with Elasticsearch in the background, it's very easy to score points when it comes to open source contribution. There are quite a lot of them. So that's a little bit about me. And with that taken care of, let's dive in. So this talk is about adding analytics to your application databases. So I think it's good to reflect a little bit about why Postgres. And it's not that hard to answer, but it's good to quantify it. So today, when you start an application, be it an e-commerce web shop or an application or some website, and you want to store your data somewhere, you will typically go and look for what we call transactional database. If you one flavor can be MongoDB, if you want to do something special or go at a certain scale, but more often than not, you just use a normal SQL-driven database, and the choice these days is pretty obvious. It's basically Postgres. And the reason is it's not so hard. It's open source. It's been out there for ages. It's been used by everyone. It's super stable. It gets more and more features. It can do pretty much everything you need. So it becomes really popular. For example, it won, I think, twice in a row the database ranking that Stack Overflow does. So pretty much there is no real reason why not to go with Postgres. So you go with Postgres and you build your application and it does great for you and everything is good. And then at some point you want to know, how is my website doing? Like, how many users do I have? How do I splice my users based on maybe something they'll put in their shopping cart? Or maybe how many users, what was the total spend of users that ended up buying a very specific product? And that will drive your business, like, for example, selecting a loss leader or something of that sort. So you start running queries on your Postgres to that nature. And those queries are different than adding a little item to your checkout cart. It's actually analyzing activity of many users. And then you'll start finding out that Postgres is really good as an application database, but it has limitation when it comes to analytical queries and analytical workloads. And it misses key features in that space. The way it stores data is not necessarily aimed at analytics. If you run a query, the query is not executed itself in parallel, right? And in short, it's basically designed to run many small queries that touch a few rows, but it's not really designed to run a single query that touches many rows, okay? Which brings us to a main key distinction in database land: analytics versus transactional, or in this, as people say, OLTP versus OLAP. And here you see an OLTP elephant, or a database that's geared to do online transaction processing. Or as we said before, is a database geared to process many small queries. So in this allegory of an elephant, think about someone that's sitting in a jungle, has lots of bottles, and is capable of handing out their bottles one by one to whoever comes along, and really fast. Okay, so as long as a lot of people come in, they'll get their bottles and be happy, and we have a lovely party. But that's very different than what happens when you actually set up your jungle party and you need to bring all that beer there. And then you probably want to be someone like this, right? Which is an online analytics processing database. At which point you probably want to carry all those bottles together and not one by one. You want to and you need special tools to do it. You need to have crates. You need to have a harness. You need to do things differently, basically. So there is a fundamental difference between databases that are geared to do many small queries processing versus databases that are geared to do analytics. And because Postgres is optimizing for the first case, it's no surprise that it runs into trouble in the second case. So with that distinction in mind, let's see how we solve this problem. As we said, PG-DuckDB is a Postgres extension that wants to bring analytical capabilities to Postgres. And we do so by adding an engine called DuckDB. And we also connect that DuckDB instance to MotherDuck, which is a cloud offering around DuckDB, which then you can use to access BI tools and give more resources to your analytical workloads. Now, If you were me and you heard all these text, you would pretty much be in this situation. Like, what? So many things, so many stuff, right? So the goal of this presentation is to slowly go through everything I just said, piecemeal, one at a time, and with the hopefully we can clarify what's the intention there. So to start, let's talk a little bit about DuckDB. Like Postgres, you know, maybe you know DuckDB as well, but it's good to kind of reflect on it. So DuckDB is a spin-off from the Dutch Research Institute for Mathematics and Computer Science. It was in Amsterdam. It was created by these two lovely guys. No intention to relevance to all the elephants and ducks pictures in this presentation. These are two genuinely lovely guys, and that's Hannes and Mark. Hannes was a tenured researcher in CWI, and Mark was his PhD student, and they started working on DuckDB, releasing it, first released in 2019, and then later formed a company around it called DuckDB Labs and maintained it. Okay, so DuckDB, as I said, is an SQL database geared for analytics. It's in process, it's all completely open source, and it's becoming more and more and more popular by the day. It's integrated in many, many programming languages, and you can see some downloads number from PyPy. So just to give you a little bit of position of where to put DuckDB, here's two databases that you probably know, Postgres and SQLite. Both of them are transactional, so not analytical. And Postgres is a more classical client-server approach where you have a server running somewhere on a machine, and then you use a client to connect to that server over the network. And now SQLite, on the other hand, is also transactional, geared at short interactions, but it's embedded in your processes, in your applications, on the phone, or in your Python script, or whatever it's embedded. And DuckDB aims to be in this corner, where it does things differently. It's geared toward analytical workloads, but it also is embedded in your process. And that's what makes it really powerful to integrate in all these languages, because now you can file a full database, be part of your Python script, and make your pandas much faster, or be part of your JDBC driver and integrate with all the tools that support that with little hassle, just like SQL does. So what PGDuckDB tries to do is to say, okay, Postgres is good for transactional workload, and that works great. DuckDB is good for analytical workloads, and DuckDB has also these amazing capabilities and pretty much can run everywhere. So can we put them together somehow? Or said differently, can we take Postgres and move it a little bit to the right in this chart, or quite a bit to the right, by adding some DuckDB execution powers to it? And this is what we did. So when you hear take Postgres and put it together with DuckDB, and what's the best way to do it? At least you kind of imagine, okay, we have these two people, they're very good in their own things, let them work together, have some beer, watch the sunset go, and everything is super happy. That is the first approach, or the way we thought to do it. But pretty quickly, we figured out we actually want to do something else. We want to do this thing, right? We want to say, let's have this Postgres with an elephant and put DuckDB inside and show a little bit of its capabilities. So it becomes this weird animal with one trunk and one beak, as a colleague once said. So that sounds a bit like a hack. But when you think about it, that's really what we want to do. So we want to make sure that you use Postgres, it behaves like Postgres, it looks like Postgres, it understands the Postgres syntax, but suddenly it's much more performant and much more capable of doing analytical queries. Or said differently, it's an elephant with a duck inside. And to show you proof of what's going on in the later on in the talk, here's an example query. This is a totally valid Postgres SQL query, which can run, and you can see that it reads a package file. So it's a user-original file that's stored in S3 and is geared towards doing analytics. But we'll get back to exactly the syntax later. So you take Postgres, you try to put DuckDB inside, and very quickly, it turns out that that's not as straightforward to do, even though DuckDB is super embeddable, and that's partly easy. But Postgres has been living around for I don't know how long, a few decennia, and no disrespect to older people, I'm starting to be in that category as well. But it's very different than how things are done today when you start something new, right? And so they speak very different languages. Postgres is written in C, DuckDB is C++. The error handling in Postgres is completely different than the error handling in DuckDB, which uses exception. As we said before, the query processing itself is very different. Postgres uses processes per connection, DuckDB uses threads. That means DuckDB expects multi-threaded access to things. Postgres has ways to do it, but it's not really geared toward locking. Lots and lots and lots of technical detail. So it took us a few months of doing that, sitting in labs, putting things and adding mixtures. And we're actually pretty proud of what came out. So I'm going to walk you a little bit as to how does that work. Right, as we said, we wanted to make it feel like Postgres. So let's start with a brief overview of how Postgres processes data. First, you start with a parser, so taking the SQL string and building something that's easier for computers to work with, an abstract syntax tree. Then you take that one and you start to plan it and map it to tables and understand types and understand the sizes of tables you have to work with. And then finally, once you decided how to run the query, you hand it off to the executor, which then goes and runs the queries and hopefully gives you the results. So that's Postgres. When you install PG-DuckDB, we will hook up through the Postgres extension API into a stage between the parser and the PG planner. Okay, so the parser already understood the query, so it has to be a valid Postgres query. We would like to change a few things in the parser as well and extend the language, but that's currently not possible in Postgres. So we let Postgres parse the query. Then we hook in into a custom planner that looks at the plans. If we decide to run it through DuckDB, which we'll talk about when exactly in a second, we will hand it off to DuckDB for execution. And if we decide that it shouldn't be run by DuckDB, then we let Postgres continue and do whatever it was doing before, and nothing really changes. So how do we decide? There are a few easy things, right? So we look at the query that you wrote, and if you're trying to refer to a MotherDuck table, that's obviously something DuckDB needs to handle because Postgres has no idea how to deal with MotherDuck tables, which are compatible with DuckDB. If you try to read a file like a Parquet file, which is geared toward analytics, then we also route the query to DuckDB automatically. We also took the decision when we registered a few specific table functions to read CSV and JSON in the Postgres space. And if you use one of those, obviously that will run in DuckDB as well. And finally, you can tell explicitly that all the queries in your connection should be run using DuckDB, and that you do so by setting the DuckDB force execution flag. And if any of these three are met, then the planner will route the execution to DuckDB execution, and DuckDB will use its internal vectorized engine to run analytics queries, and off we go. So, but please remember that even though those rules refer to specific DuckDB capabilities, that just has to appear in one place, or you've force settled it. It doesn't mean that DuckDB cannot refer to Postgres tables in order to read data from them. So you still have full access to your Postgres data, which is what you want to do. We want to run analytics on the data that you have stored in Postgres already. With that in mind, let's talk a little bit about what this means to your resource allocation. So here's an instance of a depiction of an instance process, and it's, as we said, it's pretty much geared toward running lots and lots of transactional queries. Very light, very small. We can do quite a lot of them. But we also say when you run analytics, you typically need to touch lots and lots and lots of data, and there is a lot to do. Okay, so those analytical queries are much, much bigger, and that practically means that there's not so much you can do concurrently, and it's also pretty much debatable how much space do you leave on the machine to process the ongoing transactional queries that are required to power your application, and that's probably why your application is then suffering, right? And you can still set up a replica, but again, the execution power of the instance is limited. So with that in mind, like here's where MotherDucks come along, and you can configure PG-DuckDB to connect to MotherDuck, and that means that MotherDuck will take over the load of executing those analytics query and run them in a dedicated DuckDB instances that we maintain in the cloud to offload your Postgres instance. So now the resources required to run each analytical queries become much smaller, much more akin to the transactional workload, and your Postgres servers is unburdened from these. So that's what MotherDuck also had. They also had a few other access utilities to access cloud resources, but I'm going to skip over those. So in short, what can we do? We put this elephant, we put it augmented with DuckDB, and now we can read and write Parquet files, right? So you also store Parquet files directly from your DuckDB instance. You can read and write CSV files into blob storage. You can also you can use the DuckDB vectorized engine to process Postgres data, or alternatively, you need some temporary space, temporary tables, in-memory tables to support multiple statements. You can create temporary tables in DuckDB in columnar store format, and finally, you can augment your local resources with MotherDuck support. So just a few examples. Say you have a Postgres Postgres table called Hacker News, where you store all the comments on Hacker News, or at least all the titles and the text, and you want to know how many posts mention DuckDB on a per year, per month basis. So that's an analytical query, and here's how you'd write it using DuckDB. First, because you refer to a Postgres table, that the PG-DuckDB will not execute this query by default using DuckDB. So that's the first command. And then you just write it, and as you'd expect, this is the answer you'll get, at least trimmed to the first few rows. So nothing special here other than the fact that it was executed through DuckDB, and we'll see later an example of how much that can matter. Here's something that's slightly more exciting. Say you want to take the data, put it somewhere in the cloud so you can connect it to your favorite BI tool and not have to worry about the impacts that it has to your Postgres service. All you need to do is to use a normal create table as select command to create the data set, but instead of using the normal syntax, you have to add using DuckDB in the command. And if you do so, that table will be created on MotherDuck, and that means that it's immediately available to connection through MotherDuck and to your BI tool, through excellent documentation that we have, generating a token, loading it, again, very straightforward as you'd expect. Going on from there, say you want to say, I want to offload my archive information, all information for Postgres, and I want to put it in MotherDuck, the same way we did before with the create table or select or some more advanced technique. And now I want to make a query that takes most of the workload from the archive that I've put on MotherDuck, but also augments it with data that's still only available in my Postgres instance. So here too, nothing really special, and that's kind of the whole point. You just union those two tables together and create an analytical query on those. And because the MotherDuck extension in DuckDB is smart enough to figure out that most of the data is in MotherDuck, then all the data that you need from Postgres will be read and uploaded from MotherDuck to do the more heavy analytical computation, and you'll get back your answer. And the last few examples is like, while you're running in the cloud, you probably want to have slightly more better access to cloud resources, especially if your Postgres is running on-premise. Then you can augment your queries with commands to access information on Blob Store. Here is an example that will take Netflix top 10 mentions and do some analysis on them. And here's another example that shows how to directly interface with an ISO repository, for example. Okay, and DuckDB has many more of those. I suggest you with the documentation, you can access these features. So to conclude, the goal of all of this was to give faster analytics on Postgres. So I think it begs the question, like, how fast is it really is? So again, we did some benchmarking. This is really much work in progress. That's where we spend most of our time to optimize and make it better and better. But just to give you a taste of what it means to move from a transactional database to an analytical database, I'll give you an example. But of course, there's no one-to example. If you run, say, primary key lookup, and you force it to be gone to DuckDB, and all the thing that DuckDB needs to go is to go to Postgres and give the single row that matches that single key, we introduce quite a lot of overhead compared to just running query against Postgres, which is exactly what Postgres was designed to do. However, if you do something much more analytical, you will see significant results. So here's an example. We use the TPC, which is a set of benchmarks using analytical research, and specifically the decision support benchmark. And that's a benchmark that allows you to generate a database of your choosing in terms of size and specify a set of queries and the correct results. So we generate 10 gigabytes worth of this data. We store it in a Postgres instance. And as common in analytics, we don't build any index scenarios on Hydras support because that data is typically refreshed often and it's too costly to add those indices. Again, very common. And then if you run the first query from the benchmark on vanilla Postgres, it will go and think about its life, try its best to give you an answer, but after 10 minutes decide it's hopeless and just give up. However, if you install PG-DuckDB and enable analytics and force execution through it, then you'll see that this very query finishes at 450 milliseconds, which is orders of magnitude faster. So just to show it, as a colleague like to say, oh, that's the easiest query optimization I've ever seen. All I need to do is install an extension rather than add indices, change the data set, denormalize the data, or whatever else you need to do. So to give you this, it gives you a taste of what it means to move from a transactional database to an analytical database when you're actually doing analytics. So that's where I wanted to finish with the presentation. Some references for follow-up.